All right, so today we have Robert Moscrop tell us about McKay quivers and how to decompose them. Take it away.
Yeah, thank you for the introduction, and thank you for asking me to do this talk. I've always enjoyed the Quiver meeting, so it's nice to be able to do one myself. So, as mentioned, I'm going to be talking about McKay quivers and how this kind of recently resurging field of decomposition gives us a way of better describing McKay quivers. And this talk is primarily based on this paper, which I had out in August with Shani Mainet, who's currently a postdoc here in Uppsala. So before I get into any kind of really technical details, let me just go through kind of the motivation of why we did this work and kind of what we're trying to show today. So without getting into any kind of heavy stuff, McKay quivers have been of use in physics for about 25, 30 years now. And this is primarily in the context of, say, strain compact applications, brain box models, but more recently also in terms of these BPS quivers and their kind of relation with higher form symmetries. So in this kind of sense, it's widely used in physics, but some of the really basic properties of these quivers are kind of poorly studied or a little unknown. An example that I won't cover today, but an illustrative one, is the automorphism groups of these quivers. Is there a relation between those and the automorphism groups of the finite group you make them from? This has only got a partial answer so far, but maybe more strikingly is this kind of property of disconnected McKay quivers. So this can occur, and it occurs very often. And yet they're not really well studied beyond these papers here by Hanani Hay, Feng and Prezas, where these kind of discuss them in a bit of a physicsy way, but really they are kind of the best description we have so far. So the kind of point of this work and why Shani and I really wanted to kind of understand this is just, one, can you start making sense of these disconnected quivers mathematically? And two, what is the physical consequence of these things? And as a spoiler, in case anyone just wants to cut to the chase, the components of a McKay quiver, you can give them definitive geometric meaning just by looking at the decomposition of these orbifold signal models. So this talk is going to be vaguely in three parts. I'm going to just review McKay quivers for those who haven't seen them before, then review a little bit of this decomposition, and then show the link and show some examples. And, if I run out of time, hopefully it's a good review of the first two things. So maybe the first thing that you could ask me if you haven't seen these things before is, what is a McKay quiver? So throughout the talk, I'm just going to denote gamma as a finite group, and V, whenever it pops up, will be a finite dimensional vector space. So the point of a McKay quiver, just from a representation theory point of view, is just you give me a representation of this group gamma, and now I want to kind of understand its relations with other representations of gamma. So the best way to do this is just to take, say, R. It doesn't have to be irreducible. It could just be any linear representation of the group. And I tensor it with rho I, so one of the irreps. And then by semi-simplicity, you get this direct sum here. So these Aij are just going to be non-negative integers, and I can just package them up into a matrix. So all I now say is that matrix is the adjacency matrix of some direct graph. And that is the definition of a McKay quiver, purely algebraically. And throughout this talk, I will call this Q gamma R.
Sorry, can I ask a question? Yeah, so the choice of R, so mathematicians sometimes talk of a canonical or a chosen one. So is there a restriction on what R has to be?
No, just from a purely representation theory point of view, I can take any representation, just any linear one.
Okay, but the ones that yield the ADE Dinkin graphs are all, they're very specific. If I took, if I took one of those classic subgroups of SU2 and chose some crazy R, that's not the usual one, what would happen?
Yeah, so I will get onto this, but the point is that in that case, you're really identifying R with the orbifold action, for example. Or in that case, you would get the Dinkin graph. But there's no reason why you could just take something else. You could take sums of these things and so on. You just get different looking graphs. You wouldn't get the same one every time.
Okay, thanks.
Thank you for the question. But it raises a good point. So this is dependent on the representation you choose. So you can get different things for different R's. And if A is symmetric, which it need not be in general, we just typically drop the orientation and just have it as an undirected graph. So it's just the basic definition. You can do this for any finite group and it's all good. So maybe the best way to kind of show this is just do a very quick example. So if I take the cyclic group Z3, which I think we can all agree is a really simple group, the representations of this thing is just given by its character table. So here you just have the first one is the trivial representation, then you have this one and its conjugate representation. So now I can choose any representation to make the quiver with, and I'll take row 1 plus row 2, which may look a bit arbitrary right now, but we'll see in a second. It's kind of related to what Andreas said. And all I have to do is invert the tensor product condition. This is just done by character theory. So you can do this, and you get this very explicit formula here. If I just plug in I and j, I'm now just going to get a matrix, and it's this matrix here. So it's symmetric, so I can drop all orientation on the graph I get, and it's this thing here. So this may look very simple, but I'm going to maybe make a bit of an overcomplication and say, this is the graph of the affine A2 graph. So this is A2 being SU3. And you might say that's just overcomplicating things, this is just a loop. But the reason why I do this is because in the case for a general Zn, you can always get this loop. You can get the an-1 affine graph. And exactly what Andreas was saying, I always have to take R to be a very specific R in this case. The R in question is going to be a faithful representation of Zn, and it has to belong to SU2. So what this yields is some kind of correspondence between these finite groups, Zn, and an-1, but with the restriction that the Zn is identified inside of SU2, basically. So the basic question here is this just a nice thing for Zn, or can I kind of associate Lie algebras to other finite groups? And this was really the original motivation of McKay in a sense. So the original McKay correspondence in the algebraic form is just that there's a one-to-one correspondence between finite subgroups of SU2 and semi-simple Lie algebras. And these finite subgroups of SU2 have been known and classified. They were classified by Klein in like 1884 or something. And the correspondence is just you take your finite subgroup of SU2, take the corresponding associated representation, and then just calculate the McKay equivalent. It's always going to be of an affine Dinkin type, and it's one-to-one between these things. And in case you haven't really seen these before, it's exactly this table here. So the groups on the left are just cyclic group, binary dihedral, binary tetrahedral, binary octahedral, and binary icosahedral. And if I plot the McKay quivers by embedding these inside of SU2, I get these things on the right-hand side. And the highlighted node is always going to be the trivial representation. Yeah.
So in your theorem before, you meant simply laced and simple.
Yeah, sorry. Yeah. Okay. Yes, AD is what I should have said. So what we now have here is basically an association between these finite subgroups of SU2 and these Lie algebras, but maybe you can argue this seems a little bit artificial, a bit synthetic. Like, yes, I get these nice quivers, but can I do anything with them? And originally this was all it was, but then after a couple of years of study, there's a geometric version of this found. And this is really kind of the useful way into studying these things in string theory, let's say. So now that I have a faithful representation of SC2, I could now consider the orbifold C2 mod gamma, and then say, okay, this is a singular space at the origin, but it doesn't really matter. I can just resolve this point. And since I'm working over a field of characteristic 0, I can always resolve this point just by blowing it up continuously. Now, what would happen is I just replace that point and I get a bunch of Riemann spheres and they intersect in some pattern. So the question is, what pattern do they intersect in? And this is exactly the geometric version of the McKay correspondence. So in 1984, these guys, Gonzalez, Sprinberg, and Verdier, carried out this kind of computation, checked in all the cases, and they found that for any finite subgroup SU2, you can find a crescent resolution of the of this orbifold, such that the exceptional divisor is just going to be a bunch of Riemann spheres, and they intersect according to this formula. So here, this CGIJ is just exactly the Cartan matrix of some Lie algebra, and the question is which Lie algebra. It's exactly this one given table. So here, originally,
the diagrams for E7 and E8, shouldn't the green node be attached differently? Maybe I misunderstand what you mean.
Sorry, you mean maybe on the other side?
Yes, exactly. For E7, it should be had to have a set 2 symmetry, and for E8, it will have no symmetry.
Okay.
different
So, yes. So if that's the case,
The
then it should
affine,
be
if you want the affine diagrams, the green should be on the left
Yeah.
and on the right, respectively.
There is a mistake here. For E6,
Okay,
Yes, sorry. I
E6
think
and
that's just a.
E6 is correct, but okay. All right, good.
7,
Just to
8,
see if we talk about the same thing. Good.
No, sorry. Yes, that's just an error from copying and pasting. So this should be here and it should be there. So
Sure,
exactly.
understood. Yeah. We should know them anyway.
No, yeah. But
well, actually,
it's all good.
for E8, it should be on the right, not on the left.
Yeah, on
Okay,
the
so
left
that
and on the
is-
right.
Yeah. So forget my error on the bottom two, and it's just pretend that I know the affine Dicke diagram for this thing. But the point is that it's in this case with the geometric version, you still get the same group. It's just you don't get the affine. This is the Cartan matrix, the genuine group, not the affine version. So this is now just
I ask, so
yeah, of course.
presumably there are many different resolutions. Are these resolutions minimal or unique in some sense?
Yes, so in this sense, this one is the minimal resolution of C2 mod gamma. And I think for crescent resolutions, these ones are unique, I think. In C3 mod gamma, the crescent resolutions, I think, are related by flops. But then if you did C4 mod gamma, there could be many different crescent resolutions. So in this case, I believe it's unique. Yeah.
Yeah, so for two folds, there's no flops, there's no choice possible. It's this
Yeah,
or
exactly. Yeah, thank you for the question. So
Sakura has a comment in the chat saying that they're unique for C2 mod ADE.
yeah, exactly. And Stefano says for 4 folds they may not even exist, which I agree with. Yeah. So yeah, thank you. So maybe one comment you can say is, okay, this is for SU2. Maybe I want to start thinking about like SU3 or SU4. And while I won't detail these generalizations, I should note that there's many. So one reformulation, which is quite popular recently, is this Ito-Reed formulation, where they try to abstractify to subgroups of SUN. And I believe this is proven for SU3, but the question of whether or not it's true in SU4 and above is still open. Maybe more like evocative is this reformulation by Bridgeland, King, and Reed. And in this sense, they totally reformulate it in terms of like coherent sheaves and K theory. And given the relation between coherent sheaves, K theory, and D-branes, this is quite a hint of what could be done with the McKay correspondence. So this is exactly what was kind of done by all of these people and many, many more. So I apologize if I've missed a reference of. And it really was more about, so you look at string theory on these backgrounds, you start looking at what happens when you do these blowups, and then you see branes wrapping certain things. We won't go into too much detail because I could spend another hour talking about these things, but it should be known. So these original works start with like kind of SU2, and then these ones here going to SU3 and start, these ones in particular that I mentioned earlier, start talking about the disconnected covers a little bit. And then this paper by Aspinwall and Plessis start to think about when you take projective representations. And this is going to be something that's kind of important for us later on. And then this is developed more and more over the years. And recently, these final two papers, which I just mentioned, start using these as BPS covers, which I mentioned earlier. But the common thread throughout all of this is that you can kind of say that McKay quivers encode the category of BPS branes. It's a very heuristic claim, but that's something that could be said. And from this perspective, it makes it very clear that we should kind of want to understand some of the more superficial properties of these covers. The automorphism groups, like I said earlier, for example, if I try to consider these things as BPS covers, the automorphism groups would tell me about the flavor symmetries. So that's something that would be nice to know just as a general close form. And then obviously the case we're talking about is what's going on when they're disconnected. If I think again about BPS covers, that means I have two totally like local sets of say branes of say BPS states that are just totally disconnected and they don't really talk to each other. So that's what we're trying to answer here.
So from the point of view of physics, if you try to increase the dimension, so from complex dimension 2 to 3, 4, and 5, you can do that, supersymmetry drops by factor 1/2. And then the formulation completely changes. for the case of 5, it's no longer complex. So even though the 5 manifold is complex, the supersymmetry is not complex. So so I'm just wondering whether such a perspective has been taken into account. So it's no longer quivers, it's quivers with superpotentials. And after
yes, so I agree with you. And what I'll kind of outline in a second is I'm going to reformulate it a little bit and talk about something else. But our main motivation is this C3 mod gamma case. And it just turns out through what we did in the paper, it seems like our description not only works for arbitrary subgroups of, say, SUM, but maybe even representations that don't necessarily belong to SUM. So what we kind of outline is a physics proof in the domain that we know and understand well, so SU2, SU3. And then it turns out that the machinery of decomposition can kind of tell us more in these senses. So maybe the physics doesn't quite match up exactly, but the McKay quiver itself still gets a description through this, let's say.
I see.
But I agree with you that it's more subtle when you increase the dimension. Yeah, thank you. So let me just kind of say what's been said in the mathematics literature about this, because maybe we could just look in a book and it has already been all described and we just get a paper out of it by translating it into kind of our language. But it turns out that really, it seems that very little has been said. It seems the mathematicians have went in a different direction with regards to this correspondence. So in the original paper of McKay, he pointed out that at least in the case of SU2, the quiver is always going to be connected if the representation you take R is faithful. So now our question is basically what goes on with unfaithful representations. And then in this paper by Happel, Prezer, and Ringel, which oddly came out the year before McKay, they showed that you can give a description to the component connected to the trivial representation. And all you do is you take your group gamma, you mod out the kernel, and then you just push down that representation to this quotient. So it's always going to be another McKay quiver for the quotient, basically. But this doesn't give us a description of, say, the other terms. And then it seems like there's been very little said in the maths literature until kind of a paper recently by Hazel Brown. Now, a lot has been said in the physics literature, I should say. The physics kind of pushed these features, but in terms of the pure kind of mathematical way of describing these things, it's not really been fleshed out. And what was done in this paper, oh, sorry, does Andreas want to ask a question?
Sorry, I wanted to ask a question. Have they said anything about what happens when R is reducible or irreducible? I mean, to me, it struck me that the AN case is obtained by picking R reducible, whereas for the rest of the DE series, it's irreducible.
So in the maths literature, they predominantly say that you just take the representation that would embed it into SU2, say SU3. Okay. And in most cases, that is reducible. But also what you could do is just consider only irreducibles. And then the quivers kind of just add together in a sense, in a certain way.
But so if you took the C2 mod Zn and you picked the irreducible irrep, then how would you ever get the AN quiver?
You wouldn't get the AN quiver, you get a different one. But if you were to compare like the row 1 and the row 2 quivers, you could then infer it by adding them together in a sense. But then what you've done is you've taken the reducible representation.
I see. Is it a superposition? Like maybe like it's chiral?
Yeah, it should be like a superposition. It should just be like layering in a sense.
Cool.
It should just follow from character theory, I think.
Okay.
It's a good point.
Thanks.
Thank you. So what Hazel Brown recently said was, not only are these things kind of not well studied, it turns out that if you do this thing for an unfaithful representation, there are components that don't arise as the standard McKay quivers of other groups. And now this is kind of interesting because it means that if I want to try and interpret these things physically, could these be a signal of different theories or something that I could get, or something more kind of intricate? And what we kind of wanted to show in this is that actually the notion in physics already understands these. Like the notion of projective quivers of Aspinwall and Plesser actually covers these. And decomposition gives you a way of saying it's always going to be a McKay quiver of something, but possibly with projective representations included. So when I say, is there an orbifold way of labeling these, I'm also now including discrete torsion and projective representations. So before I kind of get on to a shift in perspective, are there any questions about just the pure McKay quiver stuff so far? If not, I will just go on. But, please do interrupt if you have anything to say. So one thing that we wanted to do is just kind of reinterpret this in terms of just a sigma model. So just try to kind of change the perspective a little bit, because it's known in this case how decomposition works very, very easily. It's the kind of typical case of decomposition. So since I say that the McKay quivers kind of correspond to the BPS branes of orbifolds, I could also similarly say that these are the supersymmetric boundary conditions for a sigma model with a target space. That's just because I have open strings. Where can they end if it's supersymmetric? These are just supersymmetric branes. And there's been work done in the past by likes of Zabazin and Lindstrom to show that if you think about it in terms of sigma models, this is the same as what you'd get from the computations did in the 90s, just from deep brain physics. And now, if I now kind of forget about the faithfulness condition, the of gamma acting on Cn, then I shouldn't really think about Cn mod gamma as an orbifold anymore. I should actually think about it as some kind of mathematical thing called a quotient stack. Now, I don't really want to go into too much detail about what these things are because it's very intricate, but I'll just give a little motivation of why this is the right notion to think about in this case. So a quotient stack is an example of a generalized space, and you can kind of do everything you do with regular spaces with quotient stacks. You can put sheaves on them. You can say there's a notion of Calabi-Yau on it, and so on and so forth. But in particular, there's more information in the quotient stack than just say an effective orbifold sometimes. In the case of a quotient stack, you have that to each point, you associate the stabilizer of that point inside the group gamma. Now, what this means is that at any point in the stack, you can kind of look at it, it is always going to see all of gamma, even the trivially acting part. Whereas if I went to the effective orbifold, so if I was quotiented by, say, gamma modulo the kernel, I'm never going to see the kernel. So the fact that the quotient stack will always see all of gamma is kind of attractive from the McKay quiver point of view, because the McKay quiver will always see all of the representations of gamma, not just the quotient. So this is at least a hint of like why this is the correct notion to think about here. And what's really kind of useful for us in this case is that quotient stacks and sigma models with quotient stacks as the target space were quite well studied in the early 2000s by Sharp and Pantev. And they wanted to see if you could get more theories from these. If you start generalizing your notion of space, can you get different types of theories? And they ran into a few issues, in particular with cluster decomposition and seeing that there could be some violation. But really the workaround was, and this was showing this great paper by Hellerman, Henriquez, Pantev, Sharp and Ander, that there's a workaround to these issues. And this is exactly what's now known as decomposition. So I will now quickly review maybe a little bit about decomposition, and I will then link it to what our story is. But I should mention that I won't go too detailed into decomposition, but there's some great seminars by Eric, an introduction to decomposition, and I recommend people watch that if they're interested. So in a nutshell, decomposition is just a phenomenon that occurs when you have a QFT in d spacetime dimensions that possesses a d-1 form symmetry, so a very large charged objects, effectively. And what this signals is that really that the QFT shouldn't really just be thought as one QFT, but a disjoint union of many. So many theories that are like non-interacting, and this is kind of the way you work around the problems that they found in the previous work. So all of the stuff that I'll talk about today comes from basically this paper in terms of decomposition, this Hellerman et al. Paper. But I should say that this is quite general. With this work starting with, say, Sharp in 2014 and so on, there have been many cases where decomposition has been found in various dimensions. And for example, in this Tanizaki Unsal paper, it was shown that you can even get decomposition in four-dimensional Yang mills, for example. So while I won't go into detail about these, I just want to emphasize that there's a really deep story to this, and I won't go into it. But kind of the key point for us was, if you have an observable of a theory that decomposes, then that observable should really respect the decomposition. You should be able to kind of understand the decomposition at the level of that observable. And it's for this reason, we kind of would expect the category of boundary conditions also decomposes. And I should also probably say that in the case where I'm talking about these quotient stacks, I'm probably thinking of more of a generalization of the boundary conditions. I'm not just thinking about physically wrapping a manifold. I'm also thinking about, say, coherent sheaves and so on. But this is not a point that's that needs to be emphasized, I think. So this is all well and good, but maybe you could say, okay, does this actually happen? And I'll give you just an example of like the classic example of how this happens and how I can link this to our framework. So if I take D4, the dihedral group, and I just label it in this way, so here are the relations, and we've all seen D4 before. And here in this presentation, Z would generate the set, which is Z2. Now, if I want to consider this space, X modulo D4 for some manifold X, then I have to specify some kind of representation of D4 on it or some action. And I'm going to say, well, let's just say that here, the Z acts trivially. So now this is going to be an unfaithful action, and I'm going to get some kind of quotient stack here instead. So again, you could say, what X could I take here? This can be easily achieved on C3, for example. So if I just look at the character table of D4 down here, if I take row 2, row 3, and row 4, and I add them together, then this last column corresponds to the center, the Z, basically. If I add those up, I'm going to get a 3, which signals that that is trivialized in the character table. And all of the rest product together to make sure I get 1s, basically, which means that it's an SU3 representation and that this Z is trivialized. So what I can now ask is, how is this different from, say, taking an orbifold by the effective group, the Z2 cross Z2, which is just the quotient of D4 mod this center? And the way that we can probe that is by kind of doing what I mentioned earlier. I want to look at some observable and try to see what goes on with it. So if we take the torus partition function, there are other things we could try to do, but the torus partition function is a pretty nice one to see in this case. Then this is just the general expression. And if I had an effectively acting D4, then I would just write this down, I would expand all of these, and I would just get a bunch of terms that have these ZGHs in and summed over exactly the central places, basically. If you haven't seen this before, these ZGHs are just basically non-perturbative path integral contributions to this partition function. And maybe also, if you're unfamiliar with it this way, you've seen a box where it has a box and a G and H inside. But now, okay, that's if it was D4 was effectively acting. But if I could say that Z acts trivially, then what I should do is really I should impose that on the partition function as well. So I should identify Z with the identity. And if I do so, I can expand the whole thing out and I get a simplification of certain terms add together, and I get this expression down here. So we can kind of see that, look, I am summing over what seems to be a Z2 cross Z2. But is this really just the expression for the torus partition function of the Z2 cross Z2 orbifold? And there's a few ways you can see that this is definitely not the case. So first of all, the prefactor out front is 1/2. But really, if it were to be for the Z2 cross Z2, there should be a quarter. Okay, is it just 2 times it? And we can easily see again, that's not the case. If it were Z2 cross Z2, well then, because it's abelian, I'd have to sum over every group element in each term of these things. But really, this is not happening. Certain terms are missing from it. So it's not just exactly 2 copies of the Z2 cross Z2 orbifold, but is there some way I can massage this expression to make it more kind of evocative of what's actually going on? And I can kind of just bundle it up like this. So I can write it as a sum over, say, the AB or the GH. It's I think this should be GH here, sorry. Where this epsilon GH here just, it'll be 1 if it's present in the expression that I had previously, or -1 if it's missing. Right? So this is just a technical rewrite, and right now I haven't given this any physical meaning, let's say. But if I do so, then I can pick out the first term here as just the torus partition function for the Z2 cross Z2 orbifold. So the question is, what does this second term really mean? And this has been well known since the 80s. This is something to do with discrete torsion, basically. And I've written out explicitly what these epsilons are. So if you haven't seen discrete torsion before, it's basically an ambiguity in the path integral which arises whenever your group, your orbifold group, can admit projective representations. And this would result in an action of the orbifold group on the B field of string theory, or you can also think of it as some kind of embedding of a projective representation on the Chan pattern factors. This is all to say, okay, there's this effect that you can impose on your orbifold if it allows projective representations. And the result is that you get certain phases that can appear in the path integral, the partition function. And it's exactly these epsilon things. So really, writing it in this way, I see that when I take D4 to act unfaithfully in this way, I get that the partition function is just the sum of these two things, these two distinct theories. And this is like the original evidence for the fact that this theory decomposes. You think about the theory on this quotient stack as really being the theory given by the disjoint union of theories on these spaces, basically. And this is kind of the key point. The role that discrete torsion plays here is basically the source of this confusion in the maths literature about what the extra terms are in the McKay equivalent. So, okay, I've given you this example, but I've also given you the representation. Yeah, is it compatible with this basically? And we can just do the whole calculation basically. So you feed this representation into Sage or GAP, you can get this expression out, and you see that since I'm trivializing a central Z2, I get two components. And this first component is going to be the Z2 cross Z2 quiver. This is guaranteed by the thing that Happel, Puresha, and Ringel proven. And then this second thing maybe looks a little bit odd, but you could say, okay, is this maybe an n equals to 4 quiver or something just very simple? But really, this has already been shown in the past in this paper by Aspinwall and Plesser to be the McKay quiver for Z2 cross Z2 with discrete torsion. So the representation on this node is not one dimensional, it's two. And this is the key point here. If you widen your ideas of McKay quivers from linear McKay quivers to projective ones, you get a description of every single component. And in this case, it exactly matches up. So this is an exact agreement. We're good in this very, very simple case. So I'll now go through, maybe I'll just mention the general case, but if there's any questions, it might be a good time to take them now.
Should there in principle be a potential, as Ami mentioned already earlier, or is this something that has nothing to do with potentials, super potential?
Yeah, so I think you should in theory be like cautious of the potential and so on and so forth. But in our case, we're just kind of, first of all, just trying to describe the parts of the quiver first. And then the questions of like these added kind of details, like the potentials and so on and so forth, which you could maybe get from like the path algebras or the structures of these branes, are something that you can maybe consider later. And we didn't really talk about them in the paper. But it is something important to discuss.
Because this would make a crucial difference for the quiver on the right, for example, like what the potential is.
that should be reflected here. Basically. Because
it does look like n equals 4, but only with a specific potential.
You're exactly right. Yeah, it should matter. It's just we were only concerned with at least getting the shape down first and then studying it maybe later.
Okay.
Yeah.
So could you give me an idea of what the prescription is for writing down a McKay quiver for a projective representation?
Yeah, so there's a few ways of doing this. So the original way in Aspinwall and Plesser is they take a class in your H2 of the group, which basically gives you your alpha projective representations. Then what you do is you take your orbifold action, which should be linear, and you tensor it with this thing. Because it's linear, you're still guaranteed to get out another alpha projective representation. What you can then do is you have to kind of uplift it to the module point of view of representations. And instead of taking modules over the group algebra, you twist by this alpha. So you get these twisted group algebras, and then you look at modules over those things. Now, that's really technical and quite difficult to do. So in fact, these papers I mentioned earlier by Hanani, Hay, Feng, and Prezas, they did this by uplifting to a group where the linear representations of that group are in fact just the lifts of projectives of the other one. And then you play this game and you pick out each component, and they correspond to different classes of projective representations, basically. So there's one way using the module data, and there's one way by uplifting it and just doing regular McKay quiver stuff, basically. Thank you.
Sorry, another question. Oh, sorry, go ahead, McKay.
I just wanted to ask, so if you write the quiver and superpotential for C3 mod Z2 equals Z2, you find that the modular space is a union of several components. The main one is C3 mod Z2 equals Z2, and then you have subcodes of lower dimension, possibly of lower dimension. We can try and compute precisely what it is, and the unions are not necessarily. So the intersection between those spaces are not necessarily points. They could be bigger than points. So the structure is kind of complex. So it seems like those two disconnected quivers that you find may be related to the appearance of different components in the modular space. I'm just wondering if this is the case or not.
I don't think I can necessarily say that that is the case right now. Maybe it is, but I have to think about it a bit more. I think when I spoke to Shani about this a bit, and I think his claim is that the moduli spaces for these two components are kind of, I think they're the same, but like one is with discrete torsion, so it manifests in the quiver slightly differently, I think. So I think I don't know the answer to your question right now, but it'd be interesting to think about. I think.
I see. Okay.
This decomposition to me would more sound like that there is a product of moduli spaces or something like this. Is this
a product?
Is a sensible way to think about it? Or if you have such a decomposition statement, then it sounds like basically you have two independent theories. So you pick a point in the theory in the modular space one theory and a point in the modular space of the other theory. So it would not be a union, exactly. But
so maybe from the modular space point of view, that it actually is more.
But I'm not sure if this is right.
I mean, I'm not sure either. But just postulating, it sounds like that makes more sense in a way. And then the actual theories are disjoint because they don't interact. So the modular space doesn't. So that would make sense. Yeah. I think Stefano had a question. Or
yeah, sorry, maybe it's a trivial point which I've missed. Does the discrete torsion break any supersymmetry?
I don't believe so, but that's a good point. I would say no in this case.
Thanks.
Thank you.
So one question here is that on the left you have 4 nodes. Are you insisting on the ranks of each node?
Am I insisting that? No. So if I was to look at, say, the degrees of the representations here, all of the ones here are one-dimensional representations, but I don't think I make any. I don't insist anything really. So
I would say that you have 4 nodes of 1. With 1 node of 2 in the And so in total you have 4 times 1 versus 2 squared. So the operation of the discrete quotient is just combine all of those 4 nodes into a single one, and result in this particular quiver.
Yeah, it's plausible. I mean, there are obviously restrictions with the like the number of projective representations and the group you're in question. So there would be constraints that way. So
for example, if you take the case Z3 cos C3, would you get 9 nodes on the left and 9 nodes of 1 on the left and 1 node of 3 on the right?
So I think, so you'd extend that by, it depends what you're extending by, because Z3 cross Z3 has, for example, a Z3 possibility for its projective representations. So if I went to say a Schur cover, where all of the representations are just the projective lifts, basically, then I would get three distinct components. One is the Z3 cross Z3 without discrete torsion. One is with discrete torsion indexed by the first element and the second one, basically. The first one you mentioned would be exactly like you say, but I don't know the exact form of the other two. I have a program to do this, so I could run this afterwards and see if you'd like. But there would be obviously constraints by the number of conjugacy classes and so on.
I believe you get the same quiver as the right one, except that the node number will be 3.
Oh yeah, okay. I think that would probably be the case. Yeah. Yeah. Thank you.
Okay. Thank you.
Cool. Anything else just before I move on? Okay, great. So I've given you like the basic example. So this is the example that in all of the decomposition papers they kind of go through first, because it's a nice simple case, but there's quite a rich story behind all of this, and you can do this for basically any trivially acting subgroup. I will take it always to be central because it simplifies things greatly for us, but I just want to emphasize that you can do this for basically any subgroup. So if I take N being a subgroup of the center of gamma, then if I take the sigma model with this target space as this quotient stack, then it decomposes as the QFT on the stack is the QFT given like this. So here, the disjoint union are over the irreducible representations of N. And this omega hat rho is the standard notation to say that you can obtain the discrete torsion for each term by looking at the extension class defined by your trivially acting subgroup and mapping it under each irreducible representation. So maybe that's a technicality that isn't too important, but the point is that just from this, you can get the discrete torsion of each term. And when it's centrally extended like this, these QFTs always decompose in such a way where the orbifolding groups are identical on every factor. And that's a key point, because if it's non-centrally extended, then these orbifold groups could in general be different. And this is reflected in the quiver, and we give examples of this in the paper, but I won't have one today because it'll take up a little bit too much time. So our claim is, okay, this has been studied and is known to be true. Can we maybe verify this just by using representation theory and getting like a McKay quiver kind of description and trying to make a compatible formula to make sure that this is really what's happening on both the quiver side and the physics side. So here I just note the generalizations, and now I'm just going to go through some representation theory technicalities to try and just show that indeed the McKay quiver kind of perspective reinforces the decomposition. So if I have a group F here, I can always lift it and all of its projective representations to something called a Schur covering group. And it's just something that fits into this short exact sequence. And you have that this H2 fits inside not only the center of this G, but also the derived subgroup of G. So this is something called a stem extension. And the Schur covering groups are known to be a maximal such thing. You can't have stem extensions that are bigger than this, basically. But the key point is that, okay, this is some technical thing, but the linear representation theory of G is just equivalent to the projective representation theory of F, basically. So that's the key thing here. And as I mentioned earlier, this paper by Feng, Nanihe, and Prezas really used this to say this is a nice way of getting all of the projective quivers. You just lift to a Schur covering group, do all of that, and you get the projective quivers. So that's really nice. It's a great algorithm to get these things. But you can now think about this in terms of decomposition. And what they're really saying is that if I take a representation of G that trivializes this H2, then the quiver you get decomposes as the disjoint union of a bunch of quivers indexed by the discrete torsion, basically. So you have the original one and then a bunch of discrete torsion terms. And this is exactly what decomposition would predict. So this algorithm previously is really just like kind of reinterpreted this way. So this is one good point to say that things are compatible. The representation theory matches with decomposition. But can you take this any further? And in the paper that with Shani, we really wanted to see if you could actually get an expression for, say, every central extension. And we found out that actually you can basically use the Schur covering thing and obtain any possible quiver for central extensions. So the way to do that is to say, okay, first I'll start with this restricted case, which is the stem extension cases, which I mentioned. So these are the extensions on the bottom here, such that A will now lie in the center of G and the derived subgroup of G. And then it's a standard result in kind of this representation theory thing, that any stem extension is the homomorphic image of some Schur extension. So you can set up these two Schur exact sequences, and these things down here are just going to be standard Coulomb diagram maps. And then what this basically tells you is through Schur's lemma, how you can obtain the quiver for this bottom one from the top one. So Schur's lemma will basically tell you that if you take the quiver for the top thing, you can get the quiver for the bottom one just by crossing out the terms that have discrete torsion that aren't inside A, let's say. So since H2 of this is going to be abelian, you know that this actually, while it's a quotient, you can find a subgroup of it and you kind of just cross them. So for every stem extension, you can just move to a Schur extension instead, and then start crossing off the terms, as long as you know the homomorphism that kind of takes it that way. So maybe I can just show you an example. So there are these groups in the classification of the finite subgroups of SU3 called the delta groups. Now they're quite intricate, and there's this one that has 108 elements, delta 108, and about 20 conjugacy classes. So it's quite an unwieldy group. But I could say trivialize part of it and fit it into a stem extension. And this stem extension just has a Z3 trivialized, and then the effective part is Z3 times alt 4. Now, is this a Schur extension? It's not, because you can calculate this thing pretty easy. This thing is a Z6, so there's not enough here to be a Schur extension. So what we could do is we could just plot the quiver from here, or we could try to go to a Schur extension instead. So if I just take a general Schur extension, that would be some group of order 216. I could then plot the quiver for that and see what happens. So we can do that and then compare with what we'd get from just doing the quiver for this thing. So if I go to the Schur extension first and I plot the quiver, I get this this mess of 6 things. 6 things exactly because I have that Schur multiplier being Z6. So if I look at it here, I have the top left thing is the quiver I would get for Z3 times alt 4. That's exactly what you'd expect. Then if I label the generator of, say, Z6 to be Q, then I have that this bottom one here is going to be Q to the 1. This is Q to the 5. This thing here is Q squared. This is Q to the 4, and this is Q to the 5th. Sorry, this is Q to the 3. Sorry, Q to the 3 is here. And you might notice there's a pairing here between things and its inverse, basically. Now, this is something that I think would be interesting to study, but we didn't talk about it too much. But if I look at my original thing, I had a Z3 subgroup of the original H2. Sorry, does Ami have a question?
Yeah, the Schur multiplier of delta 108 is Z6, you said?
No, the Schur multiplier of Z3 times alt 4 is Z6.
I see. And of delta 108, how much is it?
I would think it's Z2, but I don't know. It's not too important. I'm going to a Schur covering group of Z3 cross alt 4, I should say. Maybe that wasn't too clear.
I see. Okay.
Yeah. So yeah, that's something I should clear up. So I'm going to a Schur covering group of Z3 cross alt 4, and then that gives me the whole Z6, and it's all of these components. But I only started with a Z3. I had a Z3 from the delta 108, basically. So how can I get it from this? And the naive guess would be, okay, these two ones on the far right, this would be Q squared and Q to the 4. That would form my Z3 that I want, my Z3 subgroup, when I add the original one. So this one here and these two, conjecturally, are my McKay quiver for the 108. And is that the case? Well, if I tell Sage to plot it, I get exactly this. So This here, if I compare it to the other one, it's just a small rearrangement of this. So they're the same. And then these two here are exactly the same. So what our method does is it just says that whenever you have a stem extension, you can write down a closed form thing. You can write it down explicitly using symbols, exactly what you'd expect. And again, it's because it follows from the Schur extension case, it's always going to be orbifolds with the same orbifold group, just with different discrete torsion. So this is again kind of a sign that you can just use these McKay quivers interchangeably with the idea of decomposition in the line. So before I just go into a summary, let me just say that in the paper with Shani, we were then able to kind of extend this to any general central extension by using a notion called isoclinic groups. So this is something that came out in like the 1950s and the classification of P groups. And was also mentioned in these papers by Feng, Hanani, and Prezas. And the idea of isoclinic groups is that groups that are isoclinic basically have the same representation theory in a way. Now, it turns out that every central extension is isoclinic to some stem extension of the same group. So you can then leverage that to kind of figure out the quivers for a general central extension by just doing the stem extension case. So really the algorithm from these papers in the early 2000s give you the Schur extension case. And then if you're persistent enough, you can get the quivers for any central extension basically. And we were able to kind of prove that this is the case for isoclinic groups and so on. So with that in mind, let me just summarize what I've said. So I hope that at least in this, I give some evidence to show that the decomposition of McKay quivers follows the same rules as the decomposition of sigma models on quotient stacks. And similarly, this kind of provides a check in the other direction. Like if you believe that they should be equivalent, we found independent representation theory ways of generating like consistent formulae for this. And this is exactly the case in the central extension case only. So while we've done this, and I think this is kind of good progress, there's still quite a lot to be done. So first of all, is there a representation theory way of doing this for non-central extensions? I believe generally this would be pretty difficult because you're no longer looking at just all the fold groups all the same. You now have things which are projected representations of differing groups appearing. And then similarly, what are the applications, particularly to maybe like the string compactification side? What can be said? Can you like think about it in terms of these maybe these generalized symmetries which have been kind of exploited recently? There's definitely a lot to be done. And with that, thank you for listening. And if you have any questions, please ask.
All right, let's thank Rob. Questions?
Very nice. Can you go back to the 6 quivers that you had?
These ones?
Yeah. So is this are they related by the symmetry between the generator of Z6 and its 5th power?
That's a good question. The thing is that the symmetry, it doesn't act very nicely on the quiver itself because you see the number of nodes change. So it's not as simple as say like a very easy manipulation on it. The symmetry actually typically arises as so in this case, if I think of it as a 2D sigma model, it arises as a one-form symmetry on non-perturbative sectors. So if I go back to this expression here with the ZGH, the one-form symmetry actually takes the ZGH and turns it to Z of ZG, like the trivially acting part. So it starts to kind of, it acts on these kind of things instead. So the question of whether or not it's manifest on the quiver is, I don't think so, but it would be interesting to probe it a little more.
But the quivers which are the same, they do correspond to two generators generating the same group.
Yeah, I believe that to be the case. Yeah. Anything else?
Yeah, I mean, it looks like the two guys on the right would be, you know, the first
A
part.
and A to the 5.
Yeah, and then the two bottom one would be the square and the fourth.
Exactly.
Yeah.
Yeah.
No, but
And
you
it's
said
A3 on top.
you said the other way, right? You said the bottom left is number 1, I think.
Yeah, sorry. So
Okay, so it's
didn't
1,
quite hear
5.
what you said.
It's 1, 5.
So yeah, so the bottom ones are 1, 5, and then on the right it's 2 and 4.
Yeah.
So it's like a genuine kind of subgroup in a sense. You could maybe relabel
So it
if you
gets
wanted
more.
and try to figure out.
The quiver is more complicated. The smaller the group is that is generated by a to the power.
Yeah,
of k.
it seems to be
I guess
that
that's
way.
the
It's
statement.
something we noticed a little in general, but didn't really dwell on it too much.
So is this a generic feature? Because also before you had that basically you have a more complicated quiver for choosing a trivial element, and then you have a less complicated quiver.
I think this is just a
trivial the
consequence of.
element is.
I think this is a consequence of just projective representations. I think the thing is that the things that lie in, say, like a subgroup. For example, let's take the second one. This one, which is like there's q to the third term or something like that.
How many nodes?
Sorry?
How many nodes?
How do I know it is? Well, it's just this one. I just know it is because I could check the number of alpha projective representations, and that would correspond to the -1 and the z to the 6. So that would be the case here. But here you see, like, because it's because say the subgroup it would generate would just be like a Z2. It doesn't have to use the whole of the Z6 in the projective representation. It's trivializing quite a lot of that Z6. So the projective representation of it, you have a lot more wiggle room in a way. In a sense, it's kind of maybe a little difficult to say, but you don't need to use the whole Z6 to get them, and therefore there's probably more projective representations that exist for them, I think. I think that's maybe a heuristic way to think about it, but there's probably a more technical way.
Very good. Do we have more questions?
Yeah, it will be very interesting to figure out if there is a superpotential here. And,
that would be something interesting. And I think it'd be also quite interesting, is there a way of, because typically I think you can get the superpotential from this A infinity structure, right? On like the category of branes. There's the notion of these coherent sheaves on quotient stacks. So in theory, you should be able to get the superpotential from the category of coherent sheaves on there. And that should then give you the superpotentials on these things, I think. It would be really interesting, I agree. Yeah, well, thank you for the questions.
Can you say what are the dimension vectors for these quivers?
So for this one, I don't know because there's a lot. I think, so in the first one here, it's all 1s and 3s, I think. Then I think the highest possible dimension you get is maybe a 6.
Okay, so sorry. So the total dimension is 19, you're saying? So 3 for the middle and...
something like that, yeah. I mean, I can't remember exactly.
Sorry, 18,
like,
I meant 9 plus.
Yeah. So this thing has to follow from Z3 cross alt 4. And I think the alternating group 4 has 1 3-dimensional representation, right? So then there's 3 for this thing, and then the rest are 1-dimensional for the one on the far left. And then the rest are of like higher dimension. There's definitely no 1-dimensional representations in the rest. That's the most I can tell you without checking a program.
Yeah, thanks.
Yeah, thank you.
I just want
More
to say
questions?
that we had a visit by the security guard. He was checking the quivers out.
Oh, nice.
Did you find a mistake?
Safety first, you know.
Safety. Okay, good. So the quivers are safe.
Well, that's good.
Okay. That puts us at ease.
Yeah.
Any more questions?
Hello. Have you tried for the real group of SP or SO2n+1?
Have I tried with SP or SO? You're asking, sorry?
Yeah. Have you tried this the same algorithm for the real group of SO and SP?
The while group, you mean?
Yeah.
Yeah.
The while group.
So,
Okay.
no, we haven't tried those, but because the thing is that we typically we want to do the quotients of we want to look at subgroups of SUNs, the main thing. So we didn't really try it, but in principle, I don't necessarily see why it shouldn't work. I mean, if you have particular examples of some subgroups, you can feel free to email me some, and I can try and use the algorithm to see what happens. But otherwise, I have nothing to really say on those cases right now.
Thank you.
Yeah. Thank you for the question.
Okay, so let's thank Rob again.
Yeah, thank you. Thank you for having me.
I'll